everyone. So today we're going to talk about Hess's law of heat summation. And what Hess's law of heat summation really talks about is how you can take delta H's, or changes in heat, from different reactions, and you can add those reactions together. You can sum them up, and you can also sum up their heats and get a total heat of a reaction. And so this heat of summation, the idea behind this is that the delta H, if we were to put it in textbook terms, the delta H for an overall reaction would be equal to the sum. And when we do sum, we'll do this Greek sigma, capital sigma, sum of the delta H of individual processes. And really the best way to see Hess's law is to kind of go through a sample problem and see what they're doing with it. And you know, when I look at a problem here, this first one that I'll do with you, we have this lead 2 chloride plus chlorine giving you lead 4 chloride. And I give you a delta H, but I don't tell you what it is. So I say that there's some delta H for this reaction, but I don't tell you what it is. And this is my overall reaction. Now, what I'm also doing is I'm giving you individual processes. I'm giving you process 1 and process 2. And somehow or other, adding up the processes 1 and 2 and getting them to equal the overall process, I should be able to also add up the delta H's. So when I look at this, I notice that in my first process, that the only thing that's really truly unique between my first process that I'll highlight here now and my overall reaction is PbCl2. Look at what I mean by that. PbCl2 is found, PbCl2 is found here, and it's found here. I don't find PbCl2 in any of the other reactions, in this case the second reaction. But the problem with the PbCl2 is that it is on the incorrect side. It should be on the reactant side, but in the process number 1, it is on the product side. So I need to reverse that. So I can reverse that first reaction. PbCl2 yields Pb plus Cl2. Now when I reverse this, the delta H also changes. Instead of it being exothermic, like this, we're now going in reverse. So now it is going to be opposite of exothermic. It's going to be endothermic. So this is going to be positive 359.4. Now I look at the second reaction. The second reaction matches up with PbCl4. There's a PbCl4 over here and a PbCl4 over here. And in this case, it's on the correct side. It's both on the product side. And so if I write this one down over here, I have Pb plus Cl2 yields PbCl4. That should be 2Cl. I didn't change anything about that reaction, so the delta H is going to be exactly as seen, negative 329.3. Now, what I should be able to do is add up the two reactions and get the overall. Well, the Pb on the left and the Pb on the right should cross out, and they do. The Cl2, one of the Cl2s will cross out with one of these Cl2s, and I'll be left with the following substances. PbCl2 on the left, Cl2 on the left, only one of them, and PbCl4. So I will have PbCl2 plus Cl2 yields PbCl4. Since I added the reactions together, I can also add together be heat of formations. So let's go ahead and do that. And we're going to have 359.4 plus a negative 329.3. And I'm going to get 30.1 kilojoules. Now, some other things to take notice of is if I decide that I'm going to double a reaction, well, then I need to double the delta H's. Let's try another reaction down here. So I give you the processes 1 and 2. This is my overall. So I need to add the processes together in order to get the overall. Now I look at the first reaction, and I notice that it has only SO2 in it. So notice the only thing that's unique in the first reaction here and the last reaction is SO2. But the thing is this, there's not the right number of SO2s. And it's also on the wrong side of the reaction. So for that first reaction, I need to do two things. I need to flip it and half it. And so we're going to get this. We're going to get, for the first reaction, it's going to become SO3 yields SO2 plus 1/2 O2. And our value is going to be positive 196, because I flipped it, divided by 2. We can figure that out when we have to do this part. Now, in my overall, I have my SO2 lined up. In my second reaction, there's nothing unique in the second reaction. There's no SO2 in the second reaction. There's an S and there is an O2. And what do you know? I just realized that S down here is unique. Sometimes there isn't something unique, but that S is unique. Here it is. S unique, S unique. I'm trying to look for something that will match up in the processes with the overall and use that as kind of an anchor so that I can figure out how to manipulate my equation. So that second equation has the S that is unique. And again, it needs to be cut in half, but not flipped because it's on the correct side, on the left side. So here we go. Let's go ahead and do that. We're gonna half that reaction. S plus 1.5 O2s yields SO3. And we're going to half our 790. We're going to keep it negative 790, but divide it by 2. Now let's double check again that our heats add up properly. So on the left side, we have S. The SO3s cross out. The O's, a half an O crosses out with a half an O over here. So we're left with O2, and then we have SO2. And that's my overall reaction. There it is. So now we need to find the delta H. So now when I find the delta H, I'm going to do my 196 divided by 2. That gives me 98. I'm going to do my 790 divided by 2. That's going to give me negative 395. And then I'm going to add them together. And when I add them together, I get negative 297 kilojoules. So there we have it. We know how to do Hess's law by adding processes. There's another part of Hess's law that I want to discuss with you, and that's sort of like a shortcut, using heats of formation. Let me define for you what a heat of formation is, because it's very specific. A heat of formation is the heat change, could be positive or negative, when, and this is very important, 1 mole, has to be 1 mole, of a compound is formed from its elements in their standard states. So you could pick any compound you want. For example, we could pick like CO2 here. CO2, it has a carbon and an oxygen making CO2. And a couple of important things. Notice I form 1 mole of CO2. Notice that I add C plus O2 because it's supposed to be in its standard state and oxygen exists as a diatomic. Now how do I use these heat of formations to do this shortcut here for this reaction? I want you to find the delta H for this reaction. I don't give you those process reactions where you have to then flip them around or change them. Instead, I'm using the heat of formation values that are here. So I have heat of formation of CO2, heat of formation of H2O, heat of formation of C3H8. The heat of formation symbol, which I didn't write on the slide here, is delta H, 0 formation. That means standard heat of formation. The shortcut looks like this. The delta H for an overall reaction, RXN, is equal to the sum, gotta work on my sum symbol, the sum of the delta H of formation of the products minus the sum delta H formation of the reactants. This is what I'm going to use to do this problem. So my products are CO2 and H2O. So my delta H of this reaction here is equal to the sum of the products. Well, I have CO2 is negative 393 kilojoules per mole, and that's 3 CO2, so that's times 3, plus my other product, H2O, which is negative 285 times 4. Those are my products minus my reactants. My reactants are C3H8, which is negative 104. Again, this is kilojoules per mole times moles for all of these. And that's times 1 mole, so that's just going to be kilojoules times 1 mole. And then notice there's no delta H for oxygen. And there's a good reason, because it is 0. Remember the heat of formation? It is 4 when a compound is formed. Since O2 is an element, it has a delta H of 0. So now if we plug these in, 393 times 3, we get negative 1179, plus 285 times 4, we get negative 1140, plus, because this is minus and minus here, so plus 104. So we would do this minus, and we get negative 2,215 kilojoules. This is my delta H for this reaction. This was the shortcut. Now, is the shortcut easier? Absolutely, the shortcut is easier, but it's not as fun. Because it's cool to manipulate reactions and get them to kind of work so that you could actually figure out what the delta H is for a reaction. It's not so cool to have to, like, I mean, it is fine, but it's not as fun. Now, we'll talk about bond energy next time, and we'll relate that, and then we'll talk about entropy also next time. But tomorrow in class, we're going to be spending a lot of time on Hess's law. All right, thanks so much for watching.